section 1.3, how to identify increasing and decreasing functions, and then relative maxima and minima. So if you're looking at a function, and we're going to look specifically at a graph, now this is just going to be a generic example, we're going to want to identify the portions of the graph that are increasing. Try to make that look like an S. Decreasing, and where the relative max and mins are. Maxima and minima are just plural of maximum and minimum. Now, it may be the case that graphs have more than one max and min. We'll talk about that. We'll talk about what the relative means too. So let's take a look at a relatively simple graph, something that looks like this, let's say. Goes down, comes back up, and it does that. Hopefully, remember that is a cubic model, something of the highest power bx cubed, right? You can see a couple of different regions of this. So I'm going to break this graph up into some different pieces. Specifically, if you look starting here at negative infinity, that is x equals negative infinity, then very small values of x, it's decreasing, right? It seems to have a negative slope. All the way up until about this point, which I'm going to call x sub 1. Why? Just because I feel like it, okay? And at that point, what have we got? We've got what looks to be a low point in the graph. Is it the lowest point? No. That is why this would be considered a relative min. Then if we continue on, the graph increases up until this point, which if you were thinking x sub 2, I think that's a good thing, right? X sub 2, which would be another, what appears to be a maximum. Is it the highest point of the graph? No, because this goes higher, but this would be a relative max. And then after that, the graph starts decreasing again. So what we want to be able to do, and this is how we do it, is identify the regions where the thing is actually increasing, decreasing, and where the relative max and min are. So this is how we do this. Given the points that I've got, we know that from here, that is from negative infinity to x sub 1. Now we can't include negative infinity, it's a constantly changing number. And at x sub 1, we're not actually looking at the graph decreasing, it's changing from decreasing to increasing. That is from a negative slope to a positive slope, which means that it must have a 0 slope at that point, so we don't include x sub 1. The graph is decreasing on that interval from negative infinity all the way up to x sub 1. Then what does the graph do? Well, it hits this, what we call a relative max, relative minimum, relative min, which is actually a point. So it's actually a coordinate. Don't be confused, but it would be at x sub 1, and I'm going to go ahead and say that that's at y sub 1. That value is y sub 1. And then after that, what does it do? Well, it goes up, meaning it's increasing from where to where? Over an interval starting, but not including x sub 1, up to, but not including x sub 2. So it would be increasing over this interval. And last but not least, it'd be decreasing again after that point, right? Oh, wait, I already missed it. We have something else happening here, a relative max at a point x sub 2, y sub 2, right? So that being said, what happens? Well, we can say then it's decreasing, so it's decreasing over two intervals, specifically starting at x sub 2 but not including it, all the way to, well, what's this x value here? It'd be positive infinity. You don't need to write positive, you could, but it'd just be infinity. Let me clean that up so it looks a little bit better. So it would be x sub 2, comma, infinity, just like that. Okay, so here's a practical use for things like Desmos. So looking at Desmos, there we go. If we've got the graph, so we've got a quadratic graph here, we can click on said graph and you'll see how some points show up. Like this does not have nice pretty zeros, but we could say that the graph is decreasing until this point. But notice how it put the little gray point, and if we click on that, we now know what that relative min is. So we have identified the relative min, and that also tells us the break point between the decreasing and increasing portions. So if we were to write for 2x squared plus 7x minus 3, what we could do for of x equals, sorry, 2x squared, jog my memory here, plus 7x minus 3, we could say that it's decreasing from negative infinity all the way to that x value. It's got a relative min at that xy, and we're going to pick those up here in just a sec, and then it's increasing on the interval what? To positive infinity. So because we know this point, negative 1.75, negative 9.125, we know that that's negative 1.75, negative 9.125. That means it's decreasing up until, now this is where you have to be careful, the x value, because this is always in terms of the x value, and then after that x value, it's increasing. Nice and simple. Okay? Now, I'm not going to run through the exact intervals for it, but if you look again here, and we look at this graph, it's another cubic, and notice with Desmos, you can click and drag, you can zoom in, right? You can use the plus or minus keys over here. You can't see them on the side, but you can also identify these points. So I've got this point right here. Now you got to be careful because there's 2 points that are really close to each other. That 0,4 is actually the y-intercept, but that point there is the minimum, and this point here is the maximum. So we'd say from here to here, the graph is decreasing, then it's increasing, and then it's decreasing again. So we could name those intervals, and it would have a relative min here and a relative max here. So hopefully that helps you in terms of identifying how to identify what the increasing, decreasing, and constant intervals are, as well as what the relative max and minimums